Thanks a lot, Barbara, for the kind introduction. So good afternoon, everybody. So indeed, today we'll try to present you all the capabilities of the ID16B beamline. And so the idea is that I will show you the different 2D to 4D X-ray nano analysis techniques that we have and trying to illustrate their use with some scientific example. So, okay, yes. So first of all, I would like to thank all the persons that are involved in the work that I will show you after in the presentation. So this includes all the former and present staff at the beamline, but also all the colleagues at the ESRF, especially from the support groups which are involved in the maintenance and the development of the beamline, but also all the scientific collaborators and also our users. So the ID16B beamline has been built, as Barbara said, in 2014 during the phase 1 of the upgrade of the ESRF, and is situated in this ID16 satellite building. So it means outside of the ring, since we are a long beamline. So in this building, there is 2 nanoprobes. There is ID16A and ID16B. So today I will focus on the ID16B beamline. So we have an experimental hutch that is at 165 meters from the source. So our source is an insertion device. And then in this experimental hutch, we focused on our beam to 50 by 50 nanometers, thanks to 2 sets of KB mirrors. So we have a grazing incidence fixed curvature 1 to work from 6 to 14 kV. And we have a multi-layer to work in a Bragg condition, to work from 17 to 33 kV. So thanks to also the different optics we have upstream in the optical hutch, we can work either in monochromatic beam or in pink beam. And as you can see on the image here below, we have some space around the sample and we are working in air. So it means that we can accommodate sample environments in order to perform in situ operando and time-resolved experiment. So we have different techniques available at the beamline that I like to separate them in 2 groups. We have what we call the scanning technique, so meaning that we will raster scan our sample with this nano beam and record different signal. And we also have the full field technique. So starting with the scanning technique, we have the X-ray fluorescence to have chemical information in the sample. And while scanning also the energy around K edge or L edge of the chemical element, we can perform XANES. We are equipped to also register the diffraction for the crystallographic phase in the sample, but also look at, thanks to the XBIC, the local electrical properties, and also using Xeol and time-resolved Xeol, looking at the optical transitions. So then the second group is in fact only one technique, which is a full field technique, and that it's instead of using the focus beam, we use this focus beam as a secondary source, and then we use the conic beam in order to perform X-ray nanotomography to retrieve the 3D internal microstructure in the samples. So all these techniques, they have the advantage that they can be actually used to, they can be applied to a large range of scientific fields and application. So you see here, there is a lot of application in the different branch of the material science, such as nanotechnology, metallurgy, ceramic, composite, energy-related materials, bio-inspired materials, also now sustainable materials. But also we can also accommodate biomedical application, environmental science, geology, geomechanics, and also we have a little bit of users coming from the art and archaeology field. So in the following presentation, I will try to give you the main characteristic of the different techniques that are available at the beamline and try to illustrate them using a scientific example from this different field covered by the beamline. So I will start with the X-ray fluorescence technique. So this technique, so we use it like in a scanning mode. So meaning that with this focus beam, we can scan in 2D or in 3D our sample. And in each point, we will record like the full fluorescence signal. So that's why we call this technique the hyperspectral imaging. And here in the table, you have like the different age that we can, I mean, the different chemical elements that we can map. So we can map them either using the piezo stage here that you see on the right. We have like so the beam is coming from the right. You have the piezo stage with the sample mounted there. And then you have the two fluorescence detector that they are in like a reflection mode and that they will collect the fluorescence signal. We can also accommodate the sample on a rotation stage in order to scan the sample. So you scan a line, you register the fluorescence in each point on the line, then you turn, and so on, in order to be able to reconstruct like a 3D slice with the fluorescence distribution, I mean, with the chemical distribution within the sample. So it's worth noting that we have like a high flux using the technique, so it allows for detection of low concentration elements. So as an example, I choose this study that was a study performed to look at the distribution of the potential toxic element in seaweeds. So basically, it means, I mean, here it's example of looking at the heavy metals nanoparticle in seaweeds, because those, let's say, organisms, they are well known in order to accumulate those PTE, but there is a remaining question in order to understand where they accumulate the heavy metals and what is the mechanism. So for this, you need to prepare your sample. So here it has been like a full process with high pressure freezing, then osmium fixation, dehydration, embedding, and zinc sectioning. And then while coming at the beamline, we can perform this first low resolution map to determine after where we will then scan with the very small beam some region of interest in order to obtain this, here you see on the right, top right, the X-ray fluorescence mapping of, for example, cobalt, copper, strontium, and so on. So I mean, the things is that with this high resolution, we are able to locate the different nanoparticles in the different parts of the cells of the organism, and not only localize them, but also be able to perform like some quantification and determine how much of those components there is into the cells. So then the result, in that case, in the case of this study, revealed that the different tier they accumulate with different patterns in some different subcellular part of the sample. And what is important is to figure out that thanks to a high flux and fast acquisition, we are able to have kind of a statistical study, meaning that there is really like looking a trend and not only looking at only one map. So coupled with the fluorescence, we can look at, for example, the oxidation state of the chemical element we localized by performing Xeyn's measurements. So at the beamline, it's possible to access from the vanadium to bromium and then to yttrium and to iodine K edge, and also some L edge. So to illustrate this technique, I decided to show you some study on solid oxide cells. So those cells, they are like ceramic cells. They are electrochemical device, either to produce electricity from hydrogen or to produce dehydrogen from the electrolysis of the water. They work at high temperature and they suffer degradation. So the degradation is the different kind. There is like a mechanical degradation, but there is also like diffusion mechanism involved, because indeed those cells, they are like a multi-layer cell. So you have like a two porous electrode and a diffusion barrier around like a dense electrolyte. And what can happen is that working under a current and at high temperature, you can have diffusion from one chemical element to another that will create some also detrimental layers at the interface between the electrodes and the electrolyte, where you have the electrochemical reaction happening. And so what we can do for that at the beamline is that first we can, using the XRF, like map the different chemical elements. So here you have like the electrolyte and the hydrogen electrode that they are represented by the strontium, the diffusion barrier that is represented by the cerium, and we find the strontium in the oxygen electrode. But what we see after like on this sample, so this cell worked during 6,000 hours, I think, something like this, is that we have like a migration of this strontium as the interface with the electrolyte, which is detrimental for the electrochemical reaction. What we also saw on the hydrogen electrode side, so we have on that side the strontium, but also here what is represented is the nickel distribution. And what we see is that with depletion of the nickel at the interfaces. But on top of that, what we try also to determine is that one of the degradation is the reoxidation of this nickel. And then by pointing in all these black spots and performing a Zeiss measurement by scanning the energy around the KH of the nickel, we were able to say, okay, in this position, I still have like a nickel metal, or here I have a reoxidation. So coupled with this fluorescence, we can like adapt some like diffraction detection. So we can also perform simultaneous measurement. So what it's important to understand or know about like this configuration as the beamline is that, so here is the picture of the setup with, we still have like the X-ray coming from the right. You recognize our two fluorescence detector. And then here we have the diffraction camera. So we work like in transmission mode. And then we can then adjust the position of the camera to adjust the current we are looking at, but we do not have a goniometer. So we can perform the measurement as it is here, so it means like in 3D, but also we can adapt the sample on the piezo stage and scan on 2D. At the moment, we're using a Frelon detector, but we have as a plan in the future to try to acquire like a much faster detector to be able to simultaneously acquire very fast map in fluorescence and in diffraction. So the example that I want to show you today about this diffraction is like a study, a geological study. So it's the samples, they were like a grain of zirconia in which there is some like inclusion. And then the idea was to understand what are those inclusion and also where they are situated. So the experiment has been performed like in 3D, so meaning that we have like the grain of zirconia, we scan along the grain, and each point we record one 2D diffraction pattern, and then you turn, you scan the line again, you turn, you scan the line again, and so on and so on. So at the end, you have like more than 12,000 diffraction patterns. And by looking and recognizing the different diffraction, let's say, phases in those patterns, and then by using also some reconstruction algorithm, then you are able to end up with this kind of slice reconstruction in which you can say, okay, I have like here in white, I have the zircon grain, and those red dots here, well, it's in fact the inclusion of some hematites that there was in those samples. So we have fluorescence, we have diffraction, but we can also adapt X-ray beam induced current. So this, it will be used in order to look at the local electrical property in the sample, and can be coupled with the fluorescence and with Xeol measurements that I will present to you afterwards. So the principle is that we will actually probe the electron that they are produced in the sample by thanks to an electrical circuit. So it means that it's the same. We will scan like in 2D point by point in our sample and record in each point the photocurrent that is produced. So here you have picture of the setup. So then we will adapt the sample on this connection. But it means that before the experiments, it's important to mount the sample in a way that is compatible with this, and also prepare this very thin electrical contact and wire bonding. So the advantage of those kind of measurements is that they are in operando condition, that we have a high resolution since we scan the sample with like a beam of 50 by 50 nanometer. As I say, we can combine with fluorescence and Xeol, and we also have a high signal to noise ratio thanks to the use of a locking amplifier that is coupled with a steel chopper blade. So as an example, here is the study of like the influence of copper on charge collection in some cadmium thorium solar cells. So here you have like a schematic of the multi-layer of the solar cells, and the measurement has been performed on the cross section. And here are the results. At the same time, you will obtain like the XBIP map, but also all the fluorescence maps. So here you have the copper, you have the cadmium, and then by correlating those maps, you are able to look at what is the impact of the localization in that case and distribution of the copper on the in fact the incorporation of the copper in the layer to the variation and the transition of the maximal charge collection in this kind of sample. So the last scanning technique is the X-ray excited optical luminescence. So it's a technique that it's a X-ray photon in and optical photon out technique. So it relates to the conversion of the X-ray that are absorbed by the material to optical photons, involving here I show involving in fact this multi-cascade process. So what we can get from that, we can have like a electronic transition, band gap information, energy, some energy level on the impurities, activator, and doping on the materials, and also some information on materials quality and defect. So just to give you an idea, in semiconductor nanoparticles, for example, the energy transfer to luminescence center, thanks to this some inelastic processes, lead to the creation of hole in the valence band and an electron in the conduction band, and then the recombination of the two will lead to the band gap emission. So it means that, I mean, this technique is really useful if you want like to study optoelectronic application, for example, all the rare earth down conversion phosphor, quantum confined semiconductors, heterogeneous materials, and so on, and for like application in the lightning technology like TV, LED, but also scintillator, batteries for perovskites, photovoltaic cells, and in telecommunication if you have like devices that they emit in the infrared. So so this is the setup that we have at the beamline. So this technique can be coupled with the fluorescence and the diffraction and the XBIC. And we remove one of the fluorescence detector that is replaced by this head that is made of like a two parabolic mirror, and then they are connected to like optic fiber. And we have two different spectrometers. So we have one spectrometer to look at the UV and visible light, and we have one in order to work in the infrared. So the main advantage of the Xeol is like we have like high resolution. We are able, thanks to the X-ray, to excite wide bandgap semiconductors, and also to detect atomic fluctuation in confined system, even if the technique is quite hungry from the photon point of view. So the example that I choose to illustrate the technique is a study about some like heterostructure that it's illustrated here. This is a SEM image of the electrostructure that I will talk about. So you have like a core of zinc germanium oxide with heterostructure of tin oxide around. So those systems, they have been like scanned by X-ray fluorescence and at the same time by Xeol. What we see when we plot the profile here is that first we have like a zinc diffusion in the heterostructure, and that the zinc diffusion is responsible for the UV emission that we see here on the Xeol map. And if we are looking at the diffraction maps, what we see is that exactly where we have that the UV emission, we have also like a concentration of a secondary crystalline phase. And by coupling those measurements with also nano-analysis at the kh of the zinc, the scientists who performed this measurement determined that the nano-analysis indicate octohedral coordination of this zinc atom in the crystallite phase. So this is a good example that show you, I mean, how we can combine the different techniques to solve like one scientific question. Because thanks to all those results of fluorescence, diffraction, Xeol, and Xanes, we are able to, I mean, all this suggests that the zinc impurity assisted process is responsible for the UV optical emission that is in fact involving secondary phases in the tin germanium oxide crystallite that we have in this heterostructure. So the Xeol, we can collect the produce luminescence, but we can also study the decay of this luminescence. And in order to have like more additional information to determine, for example, the recombination lifetime and dynamics, to also localize the contribution of some non-radiative recombination in the sample, and also give more information on the origin of the transition. So this is done thanks to the system that we have at the beamline is a spectrograph that is coupled with a street camera. So it's a setup that has been acquired and installed in the framework of the BMBM project in collaboration with the team of Karsten Roning from the University of Vienna. And on those systems, so we have different gratings for medium and high energy resolution. And we can also, as for the Xeol, couple those measurements with fluorescence and diffraction. So the only like small drawback is that for the moment the street camera is quite has low efficiency, so it's a little bit time-consuming technique. And here in the table, I just indicate what are the different filling modes that we can use with this setup. So the scientific example to illustrate this technique is the study of the dynamics of cobalt color center in the zinc oxide nanowires that you can see here on the top right. So the sample has been mounted in a helium cryostat to work at 7 kV. I will told about the cryostat later on in the presentation. And so the nanowire has been scanned, so with the fluorescence, but also with the Xeol. And what we can actually see. So on this map, what we can see is that there is a variation in the concentration on the cobalt. And then the Xeol signal that we retrieve, I mean, I always say we, but it's the scientists performing the experiment, is composed of like 3 different luminescent signals, which are the near band emission, the deep level emission, and the cobalt luminescence. Now, if we focus on the point where there is like a high concentration of cobalt, and we record then using the street camera the decay of the Xeol signal, and that we decorrelate actually the wavelength. So here we integrate the wavelengths that correspond to the cobalt luminescence there. And here we integrate the wavelengths that corresponds to the near band emission. We see that the response is completely different. And in this present case, in this present study, what they have found is that for here, for the cobalt luminescence, there is a new recombination mechanism that has been found, because in fact this we can actually decorrelate this in a two decay, like a fast decay first and then a slow decay. And the fast one is attributed to the direct ionization of the cobalt color center by the X-rays. So I finished to present you like all the scanning technique that we have at the beamline, but I will stay also on this setup in order to speak more about like some sample environments that we can offer at the beamline, especially for the example, the cryostat that I just mentioned in the example of in the scientific case illustrating the use of the time reserved zero sample setup. And so here you have like several pictures of this cryostat that we can mount on the sample stage. And you see here we have like the fluorescence detector coming on the side. So the cryostat can be used with the fluorescence, Xeol, and time resolved Xeol setup. It works between 8 and 20 kV. And what is important to know is that the technology that is used is based on the cold finger technology. So it means that there is no contact between the sample and the helium. Then the second sample environment that we can offer for like the 2D scanning at the beamline is this microcalorimeter. So it has been first used on ID13 with nano-focus X-ray diffraction, and we can also use it at ID16B. So here you have like a picture of the ship, which is a commercial one. So this ship has an active area of 100 by 100 microns. So it means that it's better to prepare the sample before the beam time in order to be able to place the sample in the active area using, for example, micro manipulator, knowing that in fact, according to some simulation, the homogeneous temperature area is a bit smaller. And then this device can be used in order to heat up the sample from 0 to 400, 450 degrees, and either using a ramp and stationary heating, or we can also apply like a fast heating with some pulse, like in a pulse mode, let's say. So to illustrate the use of this device, here is a study about like the tin segregation in a germanium tin microdisc that you can see here on the top right. So the microdisc has been mounted in the middle of the active area in the microcalorimeter. So it has been performed. This is like a 2D mapping of the 2D XRF mapping of the tin in the microdisc. And here where you have like the red spot, it's in fact a nano indentation that has been created in order to create some dislocation. And then the sample has been heat up in a pulse mode at 450 degrees. And then if we perform the XRF map after the heating, what has been seen is that indeed you have like a segregation of the tin starting from the dislocation point, which is exactly like the hypothesis of the scientists. So I will quickly take like I think 5 to 10 more minutes in order to talk about like the full field technique that we have at the beamline, which is the X-ray nanotomography. It's a technique for which we work usually in ping beam at 17.5 or 29.6 kV, even if we can accommodate other energies. So, as I said at the beginning, we use the focus spot as a secondary source, where we put like then a detectors at a fixed distance from this spot, and we are using the cone beam. And this is very practical because then, since we are using the cone beam, depending on where we put the sample, we can change the magnification. So it means the pixel size. So we work from 25 nanometer to 320, but also then the field of view. So as you can see on this image, we see like large fringes at the border of the sample. So this is because we are not working with absorption phase contrast tomography, but with a phase contrast tomography. And why this? Because it allows to image non-absorbing material. So for example, all the biological sample, but also in material science, polymer, or also lighter materials. And also because then we can look at the difference between phases that they have like low differences in density, as for example here on the left, on the duplexed steel, where we are able to discriminate ferrite from austenite. So the main acquisition mode we use to perform the phase contrast imaging is the holotomography technique, which consists of acquiring 4 times the same tomography, changing slightly the propagation distance. So according to this equation, it means for us just like moving a little bit the sample along the X-rays. Then what we do is that we align the 4 images for each angle of the rotation. And then thanks to phase retrieval calculation, we create those so-called like phase images. And then from those phase images, we use most of the time filter back projection algorithm to reconstruct the 3D volume. So what is ours to have? Well, nice video like this where you see your sample in 3D. So this is a solid oxide cell. So you see we have like the dense electrolyte, the 2 porous electrode, but not only, and that's the most important, we can actually perform quantitative analysis on those volumes, as for example, looking at the different volume fraction of the phases or the porosity, look at the tortuosity of those porosity, determine the representative volume element, and also calculate other intrinsic property you can have in your sample. And also, thanks to the cone beam, we can have a multi-scale approach. So what does it mean? It means that we are able to perform like a low resolution scan like this, where we will see, for example, in this material, the big walls that we have, and then decide, okay, I would like to zoom into the wall in order to perform a tomography with like higher resolution, in order to be able to resolve the nanostructure on within those walls. So the tomography is a non-destructive technique. The synchrotron X-ray source allows us to have like high flux and high resolution. So it means that, and it's what is shown here in this graph, that we are able to perform tomography with small pixel size and fast acquisition time. And since at the beamline we have space to accommodate sample environment, we can perform 4D imaging. So what it means, it just means that you will like perform tomography one after the other in order to be able to reconstruct 3D in function of time, and then end up with a 3D movie of the evolution of the microstructure of your sample. So the first sample environment that has been designed at the beamline in collaboration with the CMAP at the UGA Grenoble was like a high temperature furnace that is still in use. You can heat up the sample from 200 to 1000 degrees while you are performing scans. And as you can see here on the schematic drawing, the sample is rotating independently of the furnace that can be put on and up, down and up on the sample. And also, as it's maybe not so clear in the images, the furnace will move also with the sample, meaning that you can perform the multi-scale measurement as well. So the very first experiment that we performed was like sintering of glass particles. So basically we put some glass particles in a quartz capillary. We put the quartz capillary in the furnace. We heat up at 670 degrees, and then we were performing scan of 33 seconds for almost like 2 hours. And then you can see the sintering, and we were looking with high resolution at the evolution of the neck curvature between the beads. So in this furnace, you can adapt like some small devices. So this is the example of the work of the PhD of Rishi Kumar, where some like a tune tensile device has been designed. So the sample is introduced in the tensile device, so either on this version or then in that version. It's mounted on the rotation stage, and then they are introducing into the furnace. So the sample in that case was aluminum copper. The furnace was at 430 degrees C. And then we were performing like a measurement at low resolution. So looking at like the notch of at the shape of the sample to determine the strain and the strain rate within the sample a long time. And then by moving all the devices, performing high resolution to look at the microstructure, and especially like here you see like the metallic particles that we have in the matrix, but more especially looking at what we have in white here, the nucleation and growth of some cavities in the material. The sample, they can also be mounted under like a specific atmosphere. So here you have a piece of solid oxide cell that is mounted on top of the alumina rod in a capillary filled with hydrogen. And so then we introduced this sample mounting in the furnace, heating up at 850 degrees C. And then we were looking at what was happening in the sample. So this is solid oxide cell. Here we have like electrolyte in gray. So you have like, so this is zirconia. You have zirconia, all those particles in gray. The dark part, they are pores. And then in bright white, you have like the nickel oxide. And then this nickel oxide will react and will reduce, creating nanoporosity. And after you have a coarsening of this nickel metallic parts. The second setup we offer is the setup to perform in situ battery cycling, and in order to look at the electrode and particle like evolution. As for example, looking, I don't know, electron microstructure, morphological evolution, and mechanics. So there is different study that has been already performed at the beamline to look at macro cracking dynamics, delaminated area, interparticle distances, also gas generation, and SEI growth on particles. So that was the two setup we offer at the beamline, but we can also accommodate different in situ devices brought by the users. So here it's an example of like one tensile device that is being brought at the beamline to look at the damage mechanism in single fiber composite. And what I wanted also to add is that by doing all those like 4D movies, and if we want to be able to extract some quantitative data, we are performing, there is some tools existing, and I wanted to cite one of the tools that we are more and more like using, which is the SPAM software that help us to register the volumes at the different step of the in situ experiment, for example. And it not only allows to register the different volume and then have a qualitative interpretation of the data, but also to extract some quantitative analysis, and especially strain measurement. So I will conclude this webinar. It was a lot of information, I guess, and I don't know, maybe too much time. But the most important is that at ID16, we are a nanoprobe. We have a beam size of 50 by 50 nanometer. We can work in mono or in ping beam from 6 to 33 kV. We have like different scanning technique as well as 3D imaging technique that we can use either simultaneously or one after the other. And since we have high flux and also space around the sample, we can offer and also adapt in situ and time result experiments. So I would like to thank again all the persons that are involved in the life of the beamline. So ESRF colleagues, collaborators, and also scientists. And obviously, well, you for your attention. Thank you.
Right. Thank you very much.